In this tutorial, I will be discussing how influent flow rates to a wastewater treatment plant varies. To start, there are 4 different types of influent flows that may arrive at a plant. There's the sanitary wastewater, which includes residential flows. There's industrial wastewater, which comes from businesses and can be highly variable. And then there's stormwater. And there are 2 types of stormwater flow that may enter the plant. The first is just straight stormwater, which may occur if you have combined sanitary and storm sewers. These are very prevalent in older cities, but would never be designed today because of the water quality impacts associated with these. The second type of stormwater may enter the plant as II, which stands for infiltration and inflow. And this enters a plant with both combined and separate sanitary and storm. So the definition of infiltration is groundwater that enters through joints and leaks. So this is from water saturation of the soil. Inflow is direct runoff that enters the sewer system through manholes or other openings at the surface. So this is surface water is inflow and groundwater is infiltration. Now these influent flows can be very dramatic on the plant. The total volume of wastewater flows under wet weather is dependent on the nature of the sewer system, so combined versus separate. But even if a city has separate sanitary and storm sewers, II can add a significant burden on the plant. To give you an idea, the average wastewater treatment flow in the city of Lawrence is 10 to 12 million gallons per day. But on a wet weather day, when we have storms, II can cause that to jump up to 50 or 60 million gallons per day. So 5 to 6 times the normal flow, and that's with a separate sewer system. So just to emphasize what a separate storm and sewer system looks like, this is the separate system. And you'll see here that storm water goes directly to a river. And stormwater is mostly untreated. But the Clean Water Act, as you'll recall, is encouraging cities to begin offering some level of treatment here. But today, most stormwater enters the river untreated, whereas sanitary sewers will go to the wastewater treatment plant and treated wastewater to the river. Now, if you have a combined sewer system, which is present in Kansas City, in St. Louis, in Chicago, in existing large cities where the infrastructure is buried and hard to separate today, you have one pipe. And under dry weather condition, as shown here, sanitary wastewater is the main flow entering this pipe, and there's a weir or a dam here that stops the flow from exiting to the river. And so all of this wastewater will go toward the wastewater treatment plant. Under rain conditions, you have a mixture of rainwater and sanitary sewer, and that capacity overflows the weir. And so some mixture will go straight to the river. And this will be some raw sewage that enters the river. Now it will be very dilute because of the massive rain amount. But this prevents the sewer system from overflowing and backing up in people's homes. And so this is commonly referred to as a CSO, or combined sewer overflow. And this is a significant public health risk and something that the EPA really would like to prevent. And so sewer systems and wastewater treatment plants are being encouraged to increase their capacity to raise this weir up so that more of this flow would go to the wastewater treatment plant. Now, if you've taken hydrology, you're probably familiar with this hydrograph. On the x-axis, you have time and hours, and on the y-axis, you have both rainfall intensity and stream discharge. The dotted lines and the solid line here are showing stream discharge. And you have the first curve is showing you before urbanization, so stream discharge before. And you'll see here that the intensity of the stream discharge is lower and curves off longer than after urbanization. After urbanization, what occurs is we have a great deal of impervious surface such as asphalt and concrete that's paved. And so when water hits that impervious surface, it runs off directly and quickly to a river. And so you have a high peak intensity that occurs after urbanization, and that discharge leaves fairly quickly. So if we think about how this will impact a wastewater treatment plant, a similar thing occurs. So you have this really intense peak flow to the wastewater treatment plant, and then it will taper off over time. And so when wastewater treatment plants are designed, they must be designed for average dry weather flow, ADWF, average dry weather flow, but they're also designed for average wet weather flow, and then they must also be designed for the peak flow rate. And so this can vary quite a bit. So you have dry weather, wet weather, and peak. These are day-to-day differences and perhaps seasonal differences. On this graph, I'm also showing you how the daily variation changes even under dry conditions. You have flow rate entering the plant, Q0, and then you have a 24-hour day. So this is just one day. And what happens in the middle of the night when everyone's sleeping, the flow rate hits its lowest amount. And then shortly after everyone wakes up, takes a shower, uses the restroom, and then there's a travel time, but the peak to a plant typically happens before midday. And so even during a 24-hour period, you will have a great variation in the flow rate. So this is sometimes called a diurnal or daily variation. Some of this groundwater will leak into the storm system and contribute to infiltration and increased influent flows at the wastewater treatment plant. So if we look at this hydrograph again, at the wastewater treatment plant, you have the first curve here is dry weather flow. So this curve is average dry weather. And then the top curve here is showing you the hydrograph under wet weather. And what I want you to understand is that wet weather causes flow rates that are both intense and prolonged. Intense and prolonged. And this is something that you should be able to draw. So here the time scale is days. And what I mean by intense is you have an initial high peak that occurs in the plant. But the base flow rate, even after 4 or 5 days, can be slightly elevated. So this is an intense, very short-lived peak, but the base flow is elevated in a prolonged fashion. Okay, and so what you also see within this hydrograph is you still have that diurnal variation that occurs. I want to emphasize that combined sewers cause the largest problem for wastewater treatment plants, but even for separate sewer systems, II flows can be significant. They can contribute 5 or 6 times the flow, depending on the quality of the sanitary sewer. Because II increases the treatment burden at a wastewater treatment plant, most cities have an II program that attempts to repair sewer systems continuously. But this is a challenging and expensive program to run because there is so much infrastructure buried. It is hard to get to that infrastructure and to keep it tight. Now in water treatment distribution, we discussed how water treatment is positively pressured so that anytime a leak occurs, water flows out of the pipe. But in wastewater, the opposite is true. The risk here would be if water were to flow out. This could contaminate soils. And so this is not what is performed. In wastewater collection systems, we keep those pipes negatively pressured so that if there is a leak, water will flow in. This causes infiltration to always. Because of this, we will always have some infiltration in a sewer collection system by the nature of protecting public health. To just summarize this tutorial, there are 4 types of flow rates that enter a plant. Sanitary and residential contribute to dry weather flow. And then you have stormwater. Sanitary and industrial contribute to dry weather flow. The other types are wet weather flow. And these are caused by storm events, and they can either enter the system either by infiltration and inflow in a separate sanitary storm system or by stormwater collection into a combined system. Combined systems will also be subject to infiltration. Now, if you remember back to our mass balance unit, when we go to design the plant and reactors, it will be based on a mass balance that incorporates flow rate. So this is the mass balance for a continuous flow system. And you'll see here that the flow rate is really essential to applying a mass balance for design. And one of the challenges with wastewater design is that you do have such a variable flow rate.